This is a talk entitled Quantum Physics from Non-Duality. It's a representation of a talk given on the 17th of November 2013 at the Center for Sacred Sciences in Eugene, Oregon. The center has three parts to its mission. The first part is to demonstrate there is a common universal truth at the core of the world's major religious traditions. This core universal truth is the teachings of the mystics of those traditions. The second part of the mission is to foster a community of spiritual practitioners who want to follow these universal teachings of the mystics, put them into practice in their own lives. This includes practitioners, groups, meditation retreats, and so on. The third part of our mission, which relates to this talk, is to help develop a new worldview in which the truths of science and those of mysticism are seen as different ways of viewing the same underlying reality. That raises a challenge. How is it that the truths of the mystical traditions can be seen as compatible with those of science? So here's the outline of the talk. We'll start with the problem of reconciling science and non-duality. We'll look at the building blocks of science, and then we'll examine in particular the arising of the Schrödinger equation, how we can possibly see how that might naturally arise from the fundamental ground of non-duality. So let's start with non-duality. Perhaps the most concise statement of non-duality comes from Shankara's crest jewel of discrimination, where he says, "There is neither seer, nor seeing, nor seen. There's but one reality, changeless, formless, and absolute. How can it be divided?" On the other hand, we have science. Here's what Einstein has to say. "The belief in an external world independent of the perceiving subject is the basis of all natural science. Physics is an attempt conceptually to grasp reality as it is thought independently of it being observed. In this sense, one speaks of physical reality." So science as it's commonly understood is seen to be based on duality, this idea of the objective world being distinct and independent from a subjective knower, this subject-object distinction. This is also expressed famously in terms of what's called as Cartesian Dualism, the duality of matter versus mind, or subject versus object. And this brings us to the problem of non-duality, which is that basically science describes laws of an objective reality, existing independent of the perceiving subject. Whereas on the other hand, non-duality says that ultimately there is no such objective reality independent of the perceiving subject. So this is the root problem, the incompatibility between science and non-duality, is that science is rooted in this basic assumption that there is an objective reality independent of the perceiving subject, whereas non-duality teaches that all such distinctions, including the distinction between subject and object, are ultimately not real. So first of all, does quantum theory solve this problem? Well, no, it doesn't. Quantum mechanics undermines naive realism, but it does not solve this more fundamental problem. Quantum mechanics does imply that physical objects don't have definite properties independent of measurement and observation. We'll get into that in more detail in just a moment. But it does not imply that all truths of science are relative to measurement and observation. So some examples of observer-independent truths of science are conserved quantities and fundamental dynamic equations of science. So we have among the conserved quantities are, for example, rest mass, momentum, energy. Other quantities such as this are conserved. They do not depend upon observation And then the laws of physics, such as Newton's laws in the context of classical physics, and for example the Schrödinger equation of quantum mechanics, these in their own context are considered observer independent. The Schrödinger equation is a scientific truth that is not dependent upon observation by an observer. Now, it is true that some things do depend upon the observer. Heisenberg said that we can no longer speak of the behavior of a particle independently of the process of observation. So quantum mechanics teaches us that measurements don't reveal objective physical properties of things, but reveal properties that arise in dependence upon particular observational choices. So, for example, an electron has a well-defined position only if we choose to measure its position, and it has a well-defined momentum only if we choose to measure its momentum. So this is often expressed in terms of Heisenberg's uncertainty principle. So if we consider a measurement choice A, which is to determine the momentum of a particle, then its position remains undetermined. So this is expressed in terms of this graph as the narrow uncertainty of the variable p, the momentum, and the spread out yellow indeterminacy in the position. On the other hand, if we were to make another measurement, choice B, which is to determine the position, in that case the momentum would remain undetermined. However, Heisenberg didn't believe that this kind of observation dependence was absolute. He said in a conversation with Einstein, "I believe just like you that the simplicity of natural laws has an objective character, that they must be a part of reality itself, not just our thoughts about reality." So Heisenberg agreed with Einstein about the objectivity of the fundamental laws themselves, even if the particular properties of electrons and other subatomic particles were dependent upon observation. But Heisenberg's idea of objectivity was with the mathematics, not with the physical properties. He said, what is really needed is a change in the fundamental concepts of physics. We'll have to abandon the philosophy of Democritus and the concept of fundamental elementary particles. And instead, we should accept the concept of fundamental symmetries, which is a concept derived from the philosophy of Plato. So his idea was that the notion of objectively existing material particles, as Democritus had proposed, is untenable, and rather the reality should be seen as a kind of order. Objectivity is the order, the laws of nature, the mathematical structure of things. And this is represented in physics in terms of symmetries and mathematical relationships. In fact, what we measure in science are quantitative predictions of the mathematical theory. We don't actually come in contact with pieces of matter. We make measurements of things. We measure their weight, we measure their velocity, their position, we measure these properties, and we match those quantitative measurements with our mathematical theories, and this is how theory and experiment talk to each other, as it were. The notion of material particles themselves is a philosophical interpretation of the mathematical theory. This is why Heisenberg emphasized the mathematics as the more fundamental aspect of science. So how can we understand science and objectivity from this perspective? Can we make sense of science without assuming that scientific laws describe an objective physical reality? We don't actually need to assume an objective physical reality to do science, it turns out. In fact, what science is considered objectively real shifts as science evolves. Perhaps science is best understood as describing an order that is independent of measurements, but that arises in dependence upon our very definition of science. So what is meant by this? First of all, let's try and understand that what we regard as real, objectively real, depends on our conceptual interpretive framework. This interpretive framework can be seen as a kind of base of reference. A simple illustration of this can be seen by comparing the heliocentric and geocentric models of our solar system. In the heliocentric model, the Sun is fixed at the center, and the planets orbit around the Sun. In the geocentric system, the Earth is at the center, fixed, and the planets and the Sun orbit around the Earth. So, in one system, the Sun is fixed and at rest while the Earth is in motion, while in the other, the Earth is fixed and at rest while the Sun is in motion. So when the paradigm shifted from the geocentric to the heliocentric model, the understanding of what was actually at rest and what was actually in motion completely reversed for the Sun and the Earth. This just illustrates that motion and rest don't objectively exist, but are defined in dependence upon our conceptual framework, or our base of reference. So what is our understanding of the origin of the order in the cosmos? Well, if we look at the scientific method itself, we see that nature doesn't dictate the scientific method to us. There's nothing in the nature of reality that requires that we view it from a scientific perspective. Now, the order or cosmos that science reveals arises in dependence upon our chosen methods of investigation. So, the beauty of science and the power of science and the utility of science is that by viewing reality through this particular lens, what it reveals are reliable, repeatable properties that are intersubjectively invariant. So those kinds of regularities of experience are very useful to know and to have, and science is our tool for isolating those particular properties. And so if we set out to identify and isolate such properties, naturally that's what science will reveal to us. So we could define science as a way of investigating reality to determine an order that exists independent of time, place, observer, and observed. The order that's revealed is dependent upon this chosen mode of investigation. So it does not have a completely independent objective existence. So the laws of science themselves, in the framework of science, exist objectively, but more fundamentally, they exist only independent upon this chosen mode of investigation, namely the scientific framework. So we define the project of science, so it reveals useful features of experience. Science is, again, like a lens that brings these invariant features into focus. And the cosmos it reveals is relative to that choice of lens. So we could say physical science is systematized knowledge relating mathematical distinctions with precise, well-defined, and standardized measurement distinctions. In other words, these mathematical distinctions are correlations between particular aspects of experience under specific predetermined conditions that are intentionally selected. So the seeming objectivity of science rests with these exact and explicit distinctions. The distinctions of mathematics are used both for the quantitative measurements and for the formulation of relations between them. There are also distinctions that relate to the measurement procedures and standards, the criteria of repeatability under specified experimental conditions. So how does this relate to non-duality? Well, we could view science as unfolding somewhat like this. The subject-object and other distinctions arise in imagination from a non-dual ground. How exactly a world arises depends on how those distinctions are drawn. And the seeming objectivity of measurements is due to conventions and standards of measurement. And the objectivity of scientific laws is due to the very meaning of science itself, which defines a lens that reveals invariant properties of experience that we then interpret as being due to objectively existing entities. So let's try and unfold this in a little bit more detail. The building blocks of science can be viewed as based on some very fundamental distinctions. First of all, we need to have appearances, or phenomena, or data. We also need to have time to talk about how things change, and we need space to talk about where things are. We need observers and measurement devices, and we need particular systems that we're going to be studying and describing scientifically. And finally, we need mathematics to precisely and rigorously define the relations and regularities between the quantitative data of our measurements. So let's start with the appearances. Consider this band of color. We start with blue on the left and green on the right, but where exactly is the distinction between blue and green? Our experience itself does not dictate to us where such a distinction must be drawn. It doesn't come with the word blue on the left and green on the right and a line at a particular location down the middle. It's up to us to choose a convention where we want to say that blue ends and green starts, to draw that line, and then clearly and explicitly communicate that. And as long as we all agree on the same convention, we can agree as to what kind of color is to be called green and what is to be called blue. And when we make such measurements, we'll have an agreement about where such distinctions should be drawn. But the point here is that such distinctions do not objectively exist in the world. They are not given to us. We are the ones that draw the distinctions in experience. And more fundamentally, even the distinction between appearances and the awareness within which appearances arise is also a distinction that is not given to us objectively. Next, let's consider time. How does time arise from non-duality? Well, in the ultimate non-dual realization, appearance is not really distinct from awareness, but once we accept appearance as distinct from awareness, the sense of time arises, because the other of the appearance is imagined to be an absence that is prior to it, and an absence that is after it. So something arises, and if that is seen as a distinct something, then there's the notion of it having not been there previously. And if it fades away, there's the notion of it no longer being there. So there's a contrast here that creates a notion of before and after. And so the seed of time lies in this fundamental distinction between an appearance and the lack of an appearance. And from this unfolds the whole view of objects existing in time. And when this is made rigorous by the use of measurements using standardized clocks and so on, one can obtain quantifiable time. Just as we can agree on conventions for distinguishing blue and green, we can agree on conventions for measuring the passage of time. And then we can start developing a science that includes the notion of time to quantify change. Next, let's consider space. How does space arise from non-duality? Again, in the ultimate non-dual realization, appearance is not really distinct from awareness. But once we accept appearance as distinct from awareness, space arises with that. The other of the appearance is imagined as a space that's outside of it and containing it, as it were. So the notion of a distinct, limited object necessarily creates a contrast with the space surrounding it that it is not. So this is really the seed of space, and from this fundamental proto-space, you might say, unfolds the whole view of objects existing in space And when this is made rigorous by the use of measurements using standardized rulers, one obtains quantifiable space, a metric space, a space where things have quantifiable measurements and distances between them. So now we have appearances in space and in time, and we're well on our way to being able to start doing empirical science. We will also need observers or standardized measurements. Now when an appearance arises and it's identified, that implies that its absence is implicitly remembered. In ultimate non-dual realization, appearance is not really distinct from awareness, but once we accept the appearance as distinct from awareness, this notion of observation arises. A cognition of the appearance and its absence is a kind of primitive observation. We see something and its absence implies that its presence is remembered. So from this unfolds the notion of scientific observation or measurement that records results, remembers them, the properties of what is observed. I saw this and now it's gone. This arose and I can identify it. I can cognize that as a definite type of object. This implicitly implies a kind of cognition, a kind of measurement or registration of something, and at a very primitive level, of course. Now in science, we need to make this more standardized and rigorous and repeatable with instruments. So scientific measurement requires that separate observations are performed in the same way so the results can be coherently related to each other. And only by imposing such order on the observer is it possible to reveal an order in the observed. If we had a telescope, for example, and the base was wobbly, it was out of focus, there would be no rhyme or reason to what was observed through it. So in order to make repeatable observations, we need to impose constraints on our method of observation. We need this stable base to the telescope. We need the lens to be polished and in focus. We need to point it in a particular place. It is only by specifying these conditions of the measurement itself that we are able to consistently observe objective order. So we could say scientific observation is well-defined, standardized, consistent observations. And this is facilitated through the use of measurement devices that are calibrated to universally agreed upon measurement standards. And only then can the results be consistent, repeatable, and thereby related to each other to reveal a kind of deeper order. So the order imposed upon the observation gives rise to the order revealed in the observation. Now the observed, or the system under study, is most fundamentally an appearance. It's identified by isolating it with our attention from everything else. So we look up in the sky, we see a round object, and we identify that as the moon. And from this power of being able to isolate our system and distinguish it from the environment arises the ability to point our telescope exactly at that every night. We know what we're talking about. We know where to direct our attention again and again in order to make this repeatable study of that object. So from this basic notion of an object that's observed unfolds the notion of precisely localizing a system of study in time and space so that we can perform a scientific study of it. And this is done also by specifying the basic physical characteristics of the system. This principle of first beginning our scientific investigation by isolating a particular system for study was expressed by Maxwell in this way. He said, "In all scientific procedure, we begin by marking out a certain region as the field of our investigations. In physical science, therefore, the first step is to define clearly the material system." Now, in addition to isolating our physical system, developing consistent ways of observing it, and having quantified notions of time and space, we also need mathematics to perform our measurements and to relate those measurements consistently to each other. So how does this arise from non-duality? Well, we can see that logic arises naturally from the act of making a distinction. This was laid out, for example, in the book Laws of Form. We can also see that arithmetic arises naturally out of making distinctions. This has been illustrated in work that I've done in collaboration with Joel. You can also see this in another way in terms of set theory. The notion of a set is basically the notion of a distinction. And set theory is one of the well-recognized foundations for mathematics. Just about every mathematical structure can be understood in terms of sets, which is to say that they are distinctions. So we're pretty confident that the rest of mathematics can also be seen as arising naturally from the notion of making a distinction. Now, in the ultimate non-dual realization, distinctions are not absolutely real. But if we understand that distinctions can nevertheless be seen to arise in a kind of symmetry-breaking process, then we can see how mathematics can unfold through a process of reification of distinctions progressively. And as distinctions are reified, more and more mathematical structure unfolds. So through the reification of a single distinction, you can have a distinction between true and false, and basic logical structures unfold from that, such as binary arithmetic. Reifying further distinctions can give rise to natural numbers and arithmetic of natural numbers. And further reification of distinctions can give rise to more and more complex mathematical structures. In this way, all of mathematics can be seen as naturally unfolding from non-duality through the reification of imaginary distinctions. Similarly, we saw that space and time and observer and observed also arise through the reification of distinctions. And so the vision here is to illustrate that it's possible to see science as naturally emerging out of a non-dual ground. So with this as kind of a preliminary context, I'd like to share with you a kind of intuitive way of seeing how quantum theory, in particular the Schrödinger equation, can be seen as flowing out of this context. So the basic law of quantum mechanics is the Schrödinger equation, and I'm claiming that this can be seen as unfolding naturally from these basic definitions and structures of science. And the following part of this presentation is inspired in large part by an article by physicist Richard Conn Henry called Quantum Mechanics Made Transparent, published in the American Journal of Physics. So our first step is to look at some basic nomenclature and notation. Let psi be the state of a system at a specified time and place. Let capital X be the observational operation or measurement performed on the system. And let small x be the result of the observation. So we have our system, psi, we have our measurement, capital X, and we have the result of that measurement, small x. So let's consider a very simple example of the quantum state where we just have two options. Let's say a particle can either be here or there, on one side of the room or the other. We represent these two options as x1 and x2. And we write down psi equals c1 times x1 plus c2 times x2. So this is a way mathematically of representing the notion of a vector in a space where one possibility is the vertical axis here, and the other possibility is the horizontal axis there. So if our particle was here, the arrow would be pointing straight up. If the particle was there, the arrow would be pointing horizontally. And the unique thing about quantum mechanics is that the state can be in a combination of these two possibilities. Normally, in classical physics and intuitively in naive realism and our common sense notions of things existing in the real world, we think of things as either being here or there. There is no such thing as a combination between the two. But in quantum mechanics, this is permitted. So in general, we could get various results whenever we make a measurement. There can be two possible results in this case. Some may be more likely than others in general, and so we have the likelihood weighted by these factors C1 and C2. If C2 is larger, it pulls the arrow more towards the there axis. If C1 is larger, the arrow will be more vertical towards the here axis. That represents a higher probability of it being measured here. So we represent the state as a combination of these two possibilities, where some might be more likely than others. And the fact that these two results are mutually exclusive when they're measured, we never measure it in both places at once, but when we do measure it, it's either here or there. And this is represented by the fact that these two axes are orthogonal to each other at right angles. So now we're just going to review a little bit of calculus here. So we're going to ask how the value of f of x changes as x changes by a little bit. So we'll consider a point on the horizontal axis, and then we'll shift it just a little bit by distance delta x, and then we'll ask what is the delta y that corresponds to that. You'll see on the left-hand graph at that point the shift in delta x results in about an equal shift in delta y, whereas on the right-hand side at a different point on the graph the same shift in delta x results in a smaller shift of delta y. And how much that function changes at a given point x along the curve depends upon the tangent line to the curve at that point. And the slope of that line is delta y over delta x. And that's just the derivative. It tells us how much vertical change results from a small horizontal change. So in terms of notation, if we shift y equals f of x slightly from x to x plus delta x, then d dx, the derivative of f of x, equals the slope at x, which is delta y over delta x. So y shifts by an amount delta y, which is equal to delta x times that slope, which is d dx f of x. So consider an operator u, which is a temporal translation of our state. It's defined in terms of an identity operator I, a generator operator h, and a small number a. Now a translation of our state psi by t plus delta t is psi plus delta t d dt psi. That's just calculus. But u by definition is the operator that also performs this translation. So u acting on the state also gives that same result. This means that h is equal to delta t over a d dt. That's the operator for temporal translation. Now delta t and a are arbitrary constants, so let's just say we choose them so that delta t over a equals IH bar. There are natural reasons for doing this, which I won't go into right at this moment. With this definition, we can write h equals IH bar ddt as the temporal translation operator. So we would write h times the state is equal to IH bar ddt times the state. And this, lo and behold, is the Schrödinger equation. It simply describes how a state changes through time. And since temporal translation is invariant, the operator h is conserved, we can call this operator energy. And what it measures is the energy of the system. Now let's consider spatial translation. Proceeding analogously, consider an operator t equals I plus EP for spatial translation with a generator p and an arbitrary small number e. Now the translation of psi by x plus delta x is psi plus delta x d dx psi. So this means that our operator p is delta x over e d dx. That's the generator for spatial translation. So if we choose delta x and e so that delta x over e equals minus IH bar, then we get p equals minus IH bar d dx as the generator for spatial translation. So this means that p applied to psi is equal to minus IH bar d dx psi. Now, since spatial translation is invariant, this operator is conserved, and we can call this momentum. And we can show that the operator of position and momentum do not commute. In other words, x times p minus p times x applied to psi is not 0. So xp is not equal to px. And this directly implies the Heisenberg uncertainty principle. So in summary, although there's no real distinction of time, space, subject, or object in pure non-dual awareness, from the subject-object distinction arises the basic forms of time and space, measurement, systems under study, as well as mathematics. And by definition, science seeks order in measurement that's invariant with respect to changes in time and space. And this leads naturally to the Schrödinger equation. Thank you very much.